You ever wonder how a vending machine just knows you've put in enough money? Or how a spell checker can instantly spot a word that isn't real? Well, the secret behind a lot of that is a really powerful but simple idea called a deterministic finite automaton, or for short, a DFA. Today, we're going to break down exactly what that means, and you'll see how these little logic machines are pretty much everywhere. Let's dive in. So before we jump into any of the jargon or the fancy diagrams, let's forget all that for a second. To really get what a DFA is, we're going to start with a machine you've probably used 100 times. By looking at something familiar, we can build our understanding of this whole concept right from the ground up. Okay, think about this for a second. A subway turnstile. It seems dumb, right? But it has to make decisions. It needs to know, should I let this person through or should I stay locked? How does it actually figure that out? What's really going on inside its little mechanical brain?
Let's just break down the logic. It's actually incredibly simple. The turnstile can only ever be in one of two conditions, right? It's either locked or it's unlocked. And it only cares about two things you can do, two inputs. You can push on the arm or you can insert a coin. And notice how predictable it is. If it's locked and you push, it always stays locked. No question. If it's locked and you put a coin in, it always becomes unlocked. Every single action has one and only one predictable outcome. And that idea, that predictability, is absolutely crucial. We're going to keep coming back to that.
So, believe it or not, that super simple turnstile example, it actually contains all the core ideas of a DFA. So now let's do something important. Let's start giving those ideas their proper official computer science names. We're going to translate our real-world analogy into something a bit more formal.
All right, so let's slap some official labels on these ideas. First off, those conditions locked and unlocked, in computer science, we call those states. They're just the different modes the machine can be in. Simple enough. Second, the actions, insert coin and push, those are the inputs. They're the things that can happen to the machine to make it change. And finally, you have the rules that connect everything, like the rule that says a coin changes the state from locked to unlocked. Those rules are called transitions. So you've got states, inputs, and transitions. Those are the three big building blocks.
Okay, now that we've got the lingo down, we can look at the official blueprint. This is how computer scientists describe any machine like this one. We use a really precise, formal definition to make sure there's absolutely no confusion. Think of it like an architect's plan for the machine. Okay, here it is, the formal definition. And I know, it looks a little intimidating with all those Greek letters, but trust me, it's not as bad as it looks. A deterministic finite automaton is officially called a five-tuple, which is just a fancy way of saying it's a list of 5 essential parts. Just think of these 5 symbols, Q, sigma, Q naught, F, and delta, as the complete recipe for building any DFA. We're going to go through each one step by step.
First up, we've got Q. This is super simple. It's just the complete list of all the possible states the machine can be in. For our turnstile, Q is just the set containing locked and unlocked. In this more abstract example you see here, it's a set of states we've just decided to call A, B, C, and D. That's it. Next is sigma. This is the machine's alphabet. It's the complete set of all the input symbols the machine even understands. For the turnstile, our alphabet was the set coin, push. For a lot of examples in computer science, you'll see a simple binary alphabet, like 0, 1. Then we have Q naught. Easy one. Every machine has to start somewhere, right? Before it's seen any input, it's just sitting in its default state. That's all this is. Our turnstile, for instance, always starts out in the locked state. For this example, we're just saying it all begins at state A. Next up is F, and this one is really important. This is the set of final or accepting states. Think of this as the win condition. If the machine runs through all its inputs and lands on one of these states, we say the input was accepted. It was a valid pattern. For our turnstile, unlocked wasn't really a goal, it was just another state. But for something like a password checker, landing in an accepting state is the entire point. In the example we're about to run, state D is going to be our one and only accepting state.
And finally, the last piece of the puzzle, delta. This is the transition function. This is the brain of the whole operation. It's the complete instruction manual. For any given state and any given input, delta tells you exactly which state to go to next. There's no guesswork, there's no maybe. That's what makes it deterministic.
All right, theory time is over. We have our blueprint with all 5 parts. Now let's actually build the machine and watch it run. We're going to feed it a string of inputs and trace its journey, one symbol at a time.
So here's the challenge for our machine. We're going to give it the input string 101. Now remember, our machine starts in state A.
The goal, the win condition, is to end up in our one accepting state, which is D. So let's trace the path and see if 101 gets us there.
Okay, here we go. We're at the starting line, state A. The very first input symbol is a 1. We look at our rule book and it tells us if you're in state A and you see a 1, you move to state B. So that's what we do. We've read the first symbol and now we're in state B. All right, next up, we're currently sitting in state B, and the next input coming down the pipe is a 0. Our rules say that a 0 from state B leads directly to state D. So we follow that path. Now we're in D, which is our accepting state, but hey, we're not done yet. We still have more input to read. So we're in state D, and our very last piece of input is a 1. We check the rules for state D, and they tell us that an input of 1 sends us over to state C. And with that, we're out of input. The string is done.
Okay, this is the moment of truth. We've processed the entire string 101, and our machine ended up in state C. So now we ask the big question, is state C an accepting state? Well, our set of accepting states, F, only has one thing in it, D. Since our final state, C, is not in that set, the string 101 is officially rejected.
Now, what we just did was kind of follow along in our heads, right? We were imagining the jumps. But there are much better, clearer ways to visualize all these rules. Let's look at the two most common ways to show the complete logic of a DFA. As we were going through that, you were probably picturing something like this, with circles for the states and arrows for the transitions. This is called a state transition diagram, and it's a fantastic, super intuitive way to see the flow of the machine all at once.
And now check this out. This is the exact same machine, just in a totally different format. This is a transition table, and it holds the exact same information as that diagram. You could just look it up. If you're in state A and get a 1, the table says go to B. If you're in B and get a 0, go to D. The diagram is great for us humans to see the big picture, but this table is how a computer would actually store and use the rules. It's the same logic, just two different ways of looking at it.
So let's wrap this up. What are the big ideas you absolutely have to remember? First, these machines are deterministic. Their path is always predictable. There's no ambiguity. Second, they work step by step, reading one symbol at a time and changing state. Third, their whole job is just to accept or reject an input string based on where they land at the very end. And finally, you can show their logic in two ways, with visual diagrams or with formal tables. That's a DFA in a nutshell. And that brings us to a final thought. We started this whole thing with a simple turnstile, but this model of computation is absolutely everywhere. It's in the logic that checks if your email address is formatted correctly, it's what runs a vending machine, and it's used in searching for text inside a document. So the real question to leave you with is this. Now that you know how these simple pattern matches work, what patterns do you think are being recognized all around you right now?